Hello, everybody. This is Johnson Wang from the Origin Technology in China. It is a startup company and more focuses on digital agriculture. This is a collaboration work with Xiaofan from UIUC. My topic is exploring hardware and software optimization for accelerating large-scale texture identification on distributed GPUs. Product traceability is the capability of tracking every aspect of manufacturing and distributing a process. Lots of technologies have been proposed to solve this kind of challenging problem. Currently, each product is attached with a QR code or an NFC chip. But all these digital ID-based solutions cannot completely solve the counterfeiting problem during the supply chain, because both the QR code and the NFC chip are easy to be duplicated or recycled and attached in another fake product. The best approach for reliable traceability is to find some natural and unique information from the product itself, which is impossible to be duplicated or counterfeited. Actually, natural texture exists in lots of the product. In ICME 2021, we first proposed a system to use texture for product traceability, similar to facial recognition. Our texture recognition also supports one-to-one verification and one-to-many searching. We selected the classical image matching technology with shift, feature extraction, and the nearest neighboring matching to perform the texture recognition. And the accuracy is also very good for commercial use. This is a typical pipeline of image matching, and the major computation is the nearest neighbor matching. The major process of nearest neighbor has two parts. The first is the distance computation, and it is the computation intensive. And the second is the top two sorting, which is the bandwidth intensive. In the following, we will solve all these problems. OpenCV library already has a CUDA implementation, but the performance is relatively low. We consider it is the baseline. In the following, we will use two metrics to evaluate our performance. The capacity is how many feature metrics can be cached in the search system's memory, and the speed is how many texture image similarity comparisons could be completed in 1 second. We totally using four approaches to achieve our searching performance. Compared to OpenCV implementation, the overall capacity is improved by 20 times, and the speed is improved by 31 times. The first optimization is to convert the pairwise distance calculation on cuBLAS implementation, as discussed by Vincent. The GMM in cuBLAS library has been well optimized by NVIDIA. The second optimization is to reduce the precision to half precision, and we found there's no accuracy loss when converted from full precision to half precision. Half precision is supported in modern NVIDIA GPUs. It can save half memory usage and 2 times fast. Half precision can also exploit the capacity of tensor core, which is introduced after Volta GPU. Experimental results in Tesla V100 card, we have 3.7 times speed up compared to OpenCV baseline. However, if we use half precision, also the GPU memory is reduced by 50%, but the speed is decreased by 12%. The major reason is that the matrix is too small to exploit the full capacity of CUDA cores or tensor cores, and involves extra full precision to half precision conversion. And we will solve this problem later. If we deeply investigate the nearest neighbor algorithm, we can normalize the shift descriptor. we can see that the whole pipeline will be simplified. But if we direct normalize the shift descriptor, the matching accuracy is largely affected. So we introduce root shift implementation. It firstly normalizes each of the shift descriptor, followed by the element-wise square root. The root shift descriptors using Euclidean distance equals to using the Herring kernels, which is good at quantifying the similarity between two probability distributions. Actually, the shift descriptor is a histogram and is naturally a probability distribution. With these approaches, we normalize the shift vectors, but the accuracy is still almost kept. After this optimization, the whole nearest neighbor algorithm is reduced to only 4 steps. The step 3 and 2 can merge into single kernel, since the last 2 plus a and the square root could be performed in place directly after the sorting to minimize data movement. Even with cuBLAS implementation, the actual computation is only about 1.3 teraflops, which is far from the GPU's peak teraflops capacity. And the major reason is that the metric is too small. Based on the low-flat model, we should increase the computation to communication ratio to explore the full capacity of GPU. So we batch the reference descriptors to increase the size of the matrix to achieve higher data reuse, which is very similar to the batch in deep learning. This page shows the batch performance. We can see that if we use the batch size of 1024 and using tensor core in V100 cut, the speed is about 86 solid images per second, with an improvement of 8.2 times comparing without batching, and 29.5 times faster than OpenCV baseline. This is a huge improvement. Even with half precision, each image needs 768 feature descriptors, and eventually needs about 0.2 megabyte GPU memory, and a single 16 gigabyte Tesla V100 GPU can only cache about 80,000 images. So we proposed the hybrid memory cache scheme by using the GPU memory as the first level cache, and the host memory as the second level cache, and performed in a FIFO way. With this hybrid memory caching scheme, the capacity of a single node with an extra 64 gigabyte host memory can be improved by about 5 times. However, the search speed is dropped by 43.9%, since a host to GPU memory copy is required if the features are cached in the host side. Since we use the host memory to enlarge the capacity, we should overlap the computation and the memory copy to boost the performance. In this paper, we use multiple CUDA streams. From this figure, we can see that the computation and the memory copy is well overlapped. From this table, we can see that using multiple streams can significantly boost the speed performance due to the bottleneck of PCI interface. The peak speed is about 47,000 images per second. For the batch size of 512, we achieved about 41,000 images per second using 8 streams, with the schedule efficiency of 87.3%, which is very close to the serial peak speed. However, more extra GPU memory is used, since each stream needs a dedicated GPU memory to store some intermediate data. In the above discussion, we assume the number of features extracted from reference and query image are the same, We carefully investigated the algorithm of ratio test after 2 nearest neighbor computation during the image matching. We found that the reference features are only used for ratio test to distinguish distinct features from non-distinct features. And usually hundreds of features are extracted in each reference texture image. So we suppose a slightly reducing feature number of reference texture image won't significantly affect the search accuracy. And the experimental results validate our assumptions. We can find a good accuracy and speed variance if we use 384 features for reference image while using 768 features for query image. The accuracy loss is very limited, but the speed is significantly boosted by 34.6%. Finally, we set up a GPU cluster in our product environment using Kubernetes. And totally, we use 14 Tesla GPU cards. And finally, this GPU cluster has a capacity of 10.8 million texture images, and the speed is about 0.87 million images per second. Thanks.